Hello everyone. This is Kenji Fuji from Chiba Institute of Technology speaking. This time I would like to make a presentation entitled Angle of Seismic Incidence Related Variation in the Peak and Cumulative Responses of Irregular Base Isolated Building Models. So let me start from introduction. Base isolation is widely applied in the seismic rehabilitation of existing buildings. Near-fault pulse-like ground motions observed in post-earthquakes have been characterized by large directivity. Guinness and Arkham pointed out that some near-fault pulse-like ground motions may cause large response in structures with long periods. Therefore, the influence of the angle of seismic incidence ASI or pulse-like ground motions on the response of an irregular base isolated building is an important issue. In the previous study, the author has investigated the influence of ASI on the response of an irregular base isolated building. In the study, the ratio of the equivalent velocities of the cumulative energy along the major and minor directions (REI) is considered to select horizontal ground motion sets with a notable directivity effect. So the following questions arise. The first question is, what is the relationship between the ratio REI and the variation in the structural response parameters caused by the changes in the ASI? The second question is, how will the degree of irregularity of a base isolated building affect the variation in the structural response? In the study, nonlinear time history analysis of two 5-story irregular base isolated building models are performed using 15 long period pulse-like ground motion records considering various ASI. So let me move to ratio of the cumulative energy input along the major and minor direction. Let me consider an isotropic 1 mass 2 degree of freedom model subjected to horizontal bidirectional excitation. Here shows the equivalent velocity of the cumulative energy input of each horizontal component. Even though the total input energy of the model is independent to ASI, the cumulative input energy of each component depends on the angle of the component considered. So the ratio of the equivalent velocities of the cumulative energy input is defined by this equation. Here is the major component, while here is the minor component. Note that the ratio REI depends on the natural period and damping ratio of the model. So let me move to buildings and ground motion data. Here shows a base isolated building model considered in this study. This is based on the former Uto City Hall. The simplified structural plan and elevation and overview are shown. In this study, the isolation layer is installed below the level Z0. In this study, two models are considered. What I am showing to you is the layout of isolators and dampers in the isolation layer. Model A, shown in the left, is a model used in the previous study. The eccentricity of the isolation layer is relatively large, while the model B, shown in the right, is the modified model by changing the layout of isolators and dampers. As a result, the eccentricity in the isolation layer of model B is smaller than that of model A. Note that the numbers of natural rubber bearings, elastic sliding bearings, and steel dampers are the same in both models. This table shows a list of the ground motion sets. Here, 50 long-period pulse-like ground motion sets from MGA West 2 are used. The pulse period ranges from 4.82 to 10.40 seconds. The scaling factor is calculated based on the pushover analysis result. The effective period of the first model response and the equivalent velocity of the hysteresis dissipated energy in a half cycle are calculated as a function of the equivalent displacement. These two graphs show the calculated results for model A. In this study, the predetermined equivalent displacement is set to be 0.30 meter. The effective period at the predetermined displacement is 3.31 seconds. The equivalent velocity of the hysteretic dissipated energy at the predetermined displacement is 0.645 meter per second. Here shows the scaled maximum momentary input energy spectrum of the ground motion sets. Here, the ground motion sets are scaled so that the equivalent velocity of the input energy V delta E at the effective period equals to the equivalent velocity of the hysteretic dissipated energy in a half cycle at the predetermined equivalent displacement. Next, the calculation of the coefficient of variation of the response parameters are explained. Here, 12 cases of nonlinear time history analysis are carried out for each ground motion set. This graph shows the peak story drift for each ASI. The horizontal axis is ASI, while the vertical axis is the response parameter. The mean of the response parameter is here, and this is the standard deviation. The coefficient of variation of the response parameter is calculated as this equation. Here, Rj is the response parameter for each ASI. So let me move to analysis results and discussions. This graph shows the variation in the peak story drift of columns on the second story. Here, the horizontal axis is the ratio REI, while the vertical axis is the coefficient of variation. You can find the location of the three columns considered here from the figure in the right. As you see, the COV in the story drift decreases when the ratio REI is close to 1. These graphs show the variation in the peak resultant displacement of the isolators. As you see, the COV due to ASI are larger in model A than that in model B. The difference in each model may come from the difference of the irregularity, that is, the eccentricity in the isolation layer of model A is larger than that of model B. This graph shows the variation in the total input energy EI and the cumulative input energy of the first model response EI1U star. As you see, the COV of the total input energy EI is negligibly small and independent to the ratio REI. Conversely, the COV of EI1U star depends on the ratio REI. These graphs show the variation in the cumulative strain energy of steel dampers. As you see, the COV due to ASI are larger in model A than that in model B. This is similar to the peak resultant displacement of isolators. So let me move to conclusions. As mentioned in the introduction, these two questions are made in this study. Then Nonlinear time history analysis of two 5-story irregular base isolated building models are performed using 15 long period pulse-like ground motion records, considering various ASI. Based on the results, these three conclusions can be made. The first conclusion is, in general, the variation of the response parameter decreases when the ratio REI is close to 1. The second conclusion is, the variation in the total input energy due to ASI is negligibly small and independent to the ratio REI. And the third conclusion is, the variation in the peak resultant displacement of isolators and cumulative strain energy of dampers due to ASI are larger when the irregularity of the base isolated building model is notable. This is the end of this presentation. Thank you very much.